Okay. Okay. All right. Okay. Good evening. So first, can you confirm whether I'm audible? Can you confirm whether I'm audible? What about the audio? What about the audio? Am I audible? Anyone? Yes. Okay. Thank you. Right. Okay. So today, the plan of this discussion is this. In our 26 A-level theory batch, so we know we started fluid dynamics 2 weeks back, and we finished all theories and actually discussed few questions. I think 2 or 3 questions, right? But hereafter, now today, the plan is mainly a discussion of questions. But since it is 2 weeks before, I'll be recalling the theory parts we discussed before quickly in a very rapid manner. I'll recall the theory parts and then we are moving on to the questions, right? Since there are some new students who are also joined here for this YouTube live, if you don't have the tute, what you can do is please drop a WhatsApp message to this number, right? Then tute will be sent to you privately, right? So if you don't have the tute, repeating again, please send a WhatsApp message to this number, not a normal message, only WhatsApp, right? And I have pinned that number in a comment in the live chat as well. So you can go there and get the number, or else I have mentioned the number here, right? So prepare yourself with the tute. Prepare yourself with the tute. Right. Prepare yourself with the tute and get ready for the discussion. If you already know the theories from like Bernoulli paths, Bernoulli's theorem, continuification, and all that, you can go through again and recall what you know. And if you don't know any theories even, that will be fine, because I'll be recalling the theory parts first and then moving on to the questions. And for other students, like students who are sitting for A-levels this year, 25 batch, the importance for you of this discussion is there's a possibility of coming a fluid dynamics question, a question from Bernoulli's equation this year as the mechanics question, right, for this year level students. So therefore, for you also, you can get some benefit, get something out of this if you are still not confident enough with Bernoulli's theorem and fluid dynamics, right? So therefore, that's actually the main reason that I wanted to make this an open discussion, because anyone, if you are facing A-levels this year or 26, so that doesn't matter. Even if you are a revision student, that doesn't matter. Anyone to join this and get maximum out of this. So that's why I decided to make this open. All right. Yeah, please drop a message to that number to get the tute. Yeah, give me a second. Give me a second. The ones who has already got the dude, you can open the dude and prepare yourself for the discussion. And for others, I'll be sending it on this. Give me 2 minutes. Okay. All right, let's start. Okay, let's start. Okay, now I hope all of you have got the dude. The ones who requested the dude on WhatsApp also, through WhatsApp also, I have sent it now. Now fine, right? Okay. All right. Okay. Okay, let's start. So first, we'll see what the main theory parts here are, and then let's move on to the discussion, right? Okay. So first idea is when it comes to fluid dynamics, right? So you know what fluids are. Fluids are any liquid or gas. Fluids are any liquid or gas. See, now we are in fluid dynamics today. Fluid dynamics, right? And fluid means, you know, fluid means liquids and gases. Liquids plus gases. That is called fluid. And dynamic means moving, right? Dynamic means moving, right? So study on moving fluid of moving liquids and gases is called fluid dynamics, right? The part before this is hydrostatics. Hydrostatics means, or fluid statics means, there we are discussing about the fluids in static scenarios. Now here what we have is fluid in the motion, in the movement, right? Fluid dynamics. Fluids are liquids and gases, and we know dynamics means dynamic, kinetic means they are moving. So this is the discussion about moving liquids, right? This is the discussion about moving liquids and moving gases, right? That's the first idea. Okay, now when it comes to moving liquids, we have two types of flows. When it comes to moving liquids, moving fluids, basically, right? First one is called streamline flows, and the second type is called turbulent flows, right? Streamline and turbulent. This is the idea. Streamline flow, and we have turbulent flow. Right? Streamline and turbulent. Streamline and turbulent. Right. My audio is clear, ne? Okay. Streamline flows means Look at here. A streamline flows means if direction and magnitude, listen, if direction and magnitude of fluid particles which are passing a particular point remains constant over time, remains same, remains unchanged over time, that's called a streamline flow, right? So something like this. This is how a streamline flow is flown. And actually they flow as groups. They flow as groups like this. They flow as nicely as groups, right? And when it comes to turbulent flows means if direction and magnitude of fluid particles which are passing a particular point is changing over time, that's called a turbulent flow, right? So in reality, all flows we have are turbulent flows. There are flows which are close to streamline flows, but in the real world, we don't have 100% streamline flows, right? So these are called turbulent flows. I hope it's clear. If the velocity, the magnitude and direction of velocity, which is passing through a particular point, remains same over time, that is called a streamline flow. And if direction and magnitude of velocity which passes a particular point of fluid particles, fluid particles passes a particular point is changing over time, that is a turbulent flow, right? Okay, then here, look at here. First equation we have in fluid dynamics is continuity equation. Right. So what continuity equation says is volume flow rate through a tube, or through a medium remains constant. Now, as an example, if I consider a tube, let's say, if I consider a tube like this, and area here is, let's say, area A1, and area here is, let's say, A2, right? And velocity of fluid particles at this inlet is V1, and let's say velocity of fluid particles at the outlet V2, right? V1 and V2. Now, what continuity equation says is volume flow rates are equal, because the reason is this: if volume flow rates are not equal, what is volume flow rate? Volume flow rate is V over T. This is a volume flow rate, because anything over time is a rate. So volume flow rate is volume over time, right? Now this is actually the volume which comes into the tube per second, right? Because if there is a volume per time, volume per unit time, which means that's a volume which comes into the tube per second. Now, whatever the volume which comes into the tube per second should go out at the same time from the tube, right? So otherwise, if it doesn't go out, this flow will be harmed. So therefore, in a streamline flow, streamline flow is a nice compact flow without any gaps in between, or without any voids in between. So therefore, whatever the volume which comes in to the tube per second should go out at the same time from the tube. So therefore, volume flow rate is a constant, right? So V over T at 1 should be equal to volume flow rate at V over T at 2 outlet, right? So let's say inlet and outlet, right? So V over T at inlet is, we know this. Look at here. We know this. V can be written as, V is a volume. V here is a volume. This is a volume, right? So volume can be written as cross-sectional area into length. Volume can be written as cross-sectional area into length, right? Now, if I expand it that way, this can be written as cross-sectional area is A1. So let's say length here is L1 over T equals, and this can be written as A2, and let's say length here is L2 over T, right? Now here, what is created is L over T, L1 over T, and here also this is L2 over T. What is that? There displacement over time. Oh, that is a distance over time. Displacement over time. So that's a velocity actually. That's a velocity. So therefore, L1 over T can be written as the velocity of particles, velocity of fluid particles at that particular point. Right? Simple as that. So therefore, I'm going to substitute this as velocity. Right? Because delta L over time is a velocity. Delta L over time is a velocity. So which means we can write this as A1 V1 equals A2 V2. This is called continuity equation. This is called continuity equation. Right? That is called continuity equation. So I'm reminding these theories. If there's anyone who don't know these theories, right? So this is called the continuity equation. That is called the continuity equation. Continuity equation, right? And we can use the same result for a junction as well. What's a junction? Junction is something like this. Look at here. Junction is something like this. See? Now this is a junction. This is a junction. So let's say a liquid flows through this tube like this. A liquid flows through this tube like this. And area at this point is A1. This is A2. Let's say this is A3. Right? And velocity of particles here is, let's say, V1, and here V2, and here, let's say, V3. Right? Now, if we expand this same idea to a junction, right? If I expand this same idea to a junction, this is what comes. Same idea to a junction, na? Junction. Now, look at here. Volume comes in, right? Or the fluid comes in from these two, and fluid goes out from these two. And this is the junction. This is the junction. This is the junction. So, this is a three-way junction. This is a three-way junction, right? So, volume flow rate at inlet for the incoming fluid. Look at here. Now, to satisfy this without exploding this tube, because always the reason to have similar V over T, same V over T's, volume flow rates, is to maintain the streamline flow. So I told you clearly that in a streamline flow, there are no gaps, right? There are no voids. So it's a very nice and a very clear flow without any gaps, right? So therefore, here also, this is satisfied. This is satisfied. Incoming volume flow rate equals outgoing volume flow rate. Outgoing volume flow rate. Right? Now you know from here that volume flow rate can be written as AV. Yeah? Volume flow rate can be written as AV. So if you got any questions, if there's anything to ask, you can always put that into the chat so I can see. Right? Volume flow rate is AV now. Now I have proved V over T as AV. Now here V is a velocity. Yeah? So don't mistake this. Here V1 and V2 are velocities. V1 and V2 are velocities. Right? Yeah, I started with volumes. And now what I have proved is volume flow rate equals AV. So simply the take out of this is V over T equals AV. V over T equals AV. Right? So if anyone is volume, this is volume, but here this is velocity. Right? Volume and velocity. This is volume. Okay? Volume and velocity. So incoming volume flow rates are now from these two, 1 and 2, the liquid is coming in, incoming, right? The liquid is coming in. So which means we can write this as incoming flow rates, total incoming flow rates. A1 V1 plus A2 V2. And outgoing is only at this end. This is the outlet. Outgoing is at the outlet, right? Then that is A3 V3. So likewise, for any number of inlets or outlets also, this equation is applicable, right? 10ක් තිබ්බත් 20ක් තිබ්බත් 30ක් තිබ්බත් 100ක් outlets තිබ්බත් ඔක්කොම ටික දාන්න පුළුවන්. It's applicable, right? So whatever the volume flow rate which comes into the junction should go out from the junction. That's the idea, right? So whatever the volume flow rate which comes into the junction should go out from the junction. That's the whole idea here, right? So I used a three-way junction as an example. This is valid for any number of junctions. If you have n number of, let's say, if you have n number of inlets, then still that is valid. And you have n number of outlets, still valid. This is valid for any number of inlets and outlets. Okay. Right. So any questions from the things we discussed so far? Or is it all good? Yeah, no questions are in the chat. So I assume that's all clear up to this point, right? Next. Next. Yeah, all of you requested the route, has got the route, ne? Okay. Right. Next equation is the main equation here. That is the Bernoulli's equation. Right. When it comes to Bernoulli's equation, right? When it comes to Bernoulli's equation, listen. Bernoulli's equation, what he says is P plus half rho V squared plus rho GH. Rho GH is a constant. Right? P plus half rho V squared plus rho GH is a constant. Right? And this is pressure at a point. Pressure at a point. And this is kinetic energy. Kinetic energy per unit volume. Right? Kinetic energy per unit volume. And this is potential energy per unit volume. Potential energy per unit volume. Right? This is called Bernoulli's equation. Right? This is called Bernoulli's equation. Bernoulli's equation. Right? And there are conditions to be satisfied to apply this equation. There are conditions to be satisfied. There are actually 4 conditions. The fluid should be incompressible. These are the conditions of validity. Yeah? Fluid should be incompressible and it should be non-viscous. It should be non-viscous. Viscosity is the liquid friction. So non-viscous means there is no liquid friction in that particular liquid or particular fluid, right? Non-viscous. And next, it should be steady and stream. Steady means continuous and stream means streamline, right? These are the 4 conditions of validity of Bernoulli's equation, right? So the Bernoulli's theorem is like this. Bernoulli's theorem, this is the equation. In theorem, the equation itself is explained. The theorem is like this. In an incompressible, non-viscous, steady stream flow, the sum of pressure, kinetic energy per unit volume, and kinetic energy, potential energy per unit volume is a constant. Right? Equation එකම තමයි Bernoulli's theorem එක කියලා කියන්න තියෙන්නේ. These are keywords. So you have to add these 4 keywords and you can present the theorem, Bernoulli's theorem. Right? Theorem එකේ තියෙන්නේ මේකම තමයි. මේකම තමයි තියෙන්නේ. Equation එකම තමයි තියෙන්නේ. Equation එක තියෙන්නේ මේ keywords එක දාලා කියන්න ඕනේ. If there are no keywords mentioned, no marks will be given. Right? Simple as that. හරිනේ? Bernoulli's theorem is like this. In an incompressible, non-viscous, steady stream fluid, the sum of pressure, kinetic energy per unit volume, and potential energy per unit volume is constant. That is called Bernoulli's theorem. Right? And when it comes to this equation, this can be only applied, this can only be applied along a streamline. This can only be applied along a streamline. Equation can only be applied along a streamline. Along a streamline. Along a streamline. What is a streamline? What is a streamline? Streamline is the path traced by and then a para trace and then again and then a para the path traced by a random liquid particle which flows in the streamline flow, right? Now, when the liquid flows from here to here, we know infinite number of fluid particles flow from here to here. Then if I consider a random path for one particle like this is called a streamline. This is called a streamline, right? And this tube is called a streamline tube. This tube is called a streamline tube. The streamline tube is any tube. It carries a streamline flow. It's a streamline tube, and path traced by one particle, one random particle, which flows from one point to another point is called the streamline. So this Bernoulli's equation is only applicable through a streamline, right? So these are the basics you need to know. All right. So if there's anything, take it down. If there's anything, take it down. For students who are in the theory class, you have got the dude name, right? So I'll be discussing the same questions that I was given in the theory class. I mean, in the theory class. So if you are not a student from the theory class, from 26th theory batch, you can get the dude, right? So I think all others who are already in the theory class have got the dude, isn't it? Okay, so if there's anything to clarify before moving on to questions, up to the questions we discussed, up to this point, from the questions we discussed, up to this point, you can ask and clarify. Then we are going to start questions hereafter. These are the theories we have. Okay. Yeah, some of you are still requesting the route. Give me like a minute again. I'll be sending the route to them, and let's come back to the lesson. So go through what you have done here, and yeah, if you have any questions, it's time to ask before moving on. Okay. All right, let's move on. Right. All of you have got the root, ne? Right? Okay. Okay. Go to question 1 given in the root. Go to question 1 given in the root. Some of the details are also there. Right? Some of the details, some theory parts are also there. So most of them I explained here. Right. So go to question 1. And yeah, in theory class I discussed 3 questions. Right? In the theory class, 26 batch theory class, I discussed 3 questions. But to get the start, I'll be discussing 1 or 2 questions from here, and then let's move on to the other questions. Right? Okay. Go to question 1. Go to question 1. It says a liquid of density rho flows in a given tube. Velocities of given liquids at point A and X are V1 and V2 respectively. Obtain an equation for pressure difference between the two ends of the tube. Right. Question 1 in tube. Tube. What's the page number? Page number 2. Page 2. We are in question 1. Right. So this kind of a tube is given. Right. A tube is given. And a liquid of density rho flows through this. Velocities of given liquids at point X and Y are, okay, these points are given as X and Y. Right. Velocities are V1 and V2. Right. Velocities are V1 and V2. Right. And areas are A1 and A2. Right. That's given in the diagram. This area is A1. This area is A2. But in the first question only the pressure difference is asked. Right. For the pressure difference, no need to have the area. Let's see how it is done. Okay. Look at here. Look at here. Okay. Now, first thing is, as I told you, if you are applying Bernoulli's theorem, now, if you are a student who were in the theory class, recall these things again because I discussed this question 2 weeks back, 2 weeks back in the class. So recall again and get ready for the coming up questions because we'll be moving towards all advanced questions today in Bernoulli's theorem, and we are going to finish off all types of questions. Right. So first thing is we have to select a streamline. We have to select a streamline. Streamline is the path traced by a random fluid particle, which goes from inlet to outlet. So here I'll be selecting this as a streamline because I am interested about X and Y. So this is the line which goes through X and Y. So I'll be selecting this as my streamline now. This is the streamline. Right. And since we are dealing with energy terms, because we have kinetic energy per unit volume and we have potential energy per unit volume. Since we are dealing with energy terms, kinetic energy is per unit volume, potential energy is per unit volume, we need earth zero levels. We need earth zero level. So therefore, here I will mark earth zero level as equals 0. I will consider this streamline itself as my earth zero level. I will consider this streamline itself as my earth zero level. Okay, now this is how Bernoulli's theorem is applied. We have to have a streamline with earth zero level, and then considering 2 points on the streamline, we are going to apply Bernoulli's theorem. Right? This is how the equation is applied. Look at here. We have to mention, usually we have to mention the streamline we use. You have to mention the streamline we use. Now the streamline is the streamline which goes through X and Y. Right? By considering a streamline goes through x and y by considering a streamline goes through x and y, right? Now we have to apply Bernoulli's theorem, right? So I'm going to use points x and y, right? Now we know in Bernoulli's equation we have three components, three terms: pressure plus kinetic energy per unit volume and potential energy per unit volume. Apply that equation to this point one by one. Apply that equation to this point one by one, right? So it's like this. Now pressure at x, let's consider it as px. Pressure at x, px, right? Plus kinetic energy per unit volume, half rho v1 squared, plus potential energy by unit volume. Now it is at earth zero level, so there's no potential energy here, so that is zero. Then at y, py plus half rho v2 squared plus no potential energy here as well, zero, right? Now tell me, we know continuity equation. What it says is product AV is a constant. So that's why A1 V1 equals A2 V2, right? Since the product is a constant, if we apply the same equation for two scenarios, then we can write A1 V1 equals A2 V2, right? So product AV is a constant. So therefore, from this you can obtain A and V are inverse. A and V are two inverse properties. Which means higher the area of a tube, lesser the velocity at that end. Lesser the area, higher the velocity. Higher the area, lesser the velocity. Right? Something like that. So therefore, for sure we know that V2 is greater. For sure V2 is greater. So therefore, I'm going to subtract this in the correct manner. Then take y to this side, px minus py equals, from here you can take half rho out. When half rho is out, it is v2 squared minus v1 squared. Px minus py is the pressure difference, so which means is the final answer. You need pressure difference, right? Px minus py is the pressure difference, right? Which means now this is a positive value. You should be able to compare. Since v2 is greater than v1, this is a positive value. Since there is a positive value, from left hand side, px should be greater than py, right? Px should be greater than py. See, px is greater. Now, at the higher area, pressure is also higher. Got it? So, which means now combining all three, we can write this. Now, from this you can see pressure and area are proportionally, and from there you know area and velocity are inverse. Now, if I combine all three, which means pressure proportional to area inverse to velocity. So this is valid. This equation is valid, or this relationship is valid for anywhere, any point in fluid dynamics, right? This is valid for any point, anywhere in fluid dynamics. So I proved them using these equations and the result obtained here, right? Okay, take it down. Okay, dudes. Okay, I'll send. Take it down. And if you have any questions, you can forward them to me and get it clarified. And if you have any questions, you can hold them for the okay. Okay, let's move on. Let's move on to the next question. Okay, question two. Question two. A liquid of density rho flows through the given streamlined tube. Pressure at point x and y are px and py. Cross-sectional areas are capital A and simple A. Determine speed of the liquid at y. Okay. Before that, there's another thing that I want to highlight here is when a fluid flows naturally, always it flows from high pressure to low pressure only, right? When a fluid flows naturally, it flows from high pressure to low pressure only, right? Below this question, below this relationship, mention this. Always a fluid flows from high pressure to low pressure. Always a fluid flows from high pressure to low pressure. Always a fluid flows from high pressure to low pressure. High pressure to low pressure. Okay. So let's move on to question 2. It says a liquid of density rho flows through the given streamlined tube. Pressure at point x and y are px and py. Right. These pressures are given. And areas are different now. Pressures are px and py. Look at here. These pressures are given. So pressure at x is px. Pressure at y is py. Right. And areas are capital A and simple A. Determine speed of the liquid at y. Okay, areas are capital A and simple A. We need the speed of the liquid at y. So which means according to my label in here, what we need is V2. According to my label in here, what we need now is V2. We need V2. See, my target is V2. All right. Look at here. Now, listen first. If you are given the areas of the tube or whatever the scenario you are dealing with, areas දීලා තියෙනවා. Area එක දීලා තියෙනවා. The only way to connect area to Bernoulli's equation is through continuity equation, right? The only way to connect area to Bernoulli's equation is through continuity equation. Continuity equation එක නැතුව අපිට area එක මේකට link කරන්න බෑ. The only way to link area is through continuity equation. මේ Bernoulli and continuity equation කියන equations දෙක විතරයිනේ මේ පාඩම ඇතුලේ තියෙන්නේ, right? So in fluid dynamics you only have two equations, continuity equation and Bernoulli's equation. In Bernoulli's equation it is a relationship among pressures, right? Pressure, kinetic energy per unit volume is also pressure because any energy per unit volume is a pressure, right? Any energy per unit volume is a pressure. You can check dimensions if needed. Energy per unit volume is a pressure. So therefore that's a relationship among pressures, right? So there you have velocities, and when you are writing rho gs terms, you have height, length, everything. But there is no area in any of the terms in Bernoulli's equation. But in continuity equation, that's a relationship between area with velocity. So therefore, the only way to connect area, to plug area into Bernoulli's calculation is through continuity equation, right? Through continuity equation. So therefore, if areas are given, it's a very clear hint to use continuity equation, right? එහෙනම් areas තියෙනවා නම් අපිට කොහොමද continuity equation එක දාන්න වෙනවා, right? Look at here. Look at here. Now, since areas are given, we can use continuity equation. First, I'm going to use continuity equation. Using continuity equation, right? You can apply a1 b1 equals a2 v2 and apply it here. A1 is capital A and v1 is v1, a2 is simple A, v2 is v2. Now, as a habit, listen, as a habit, always subject the unwanted term from continuity equation, right? Unwanted term from continuity equation, because when we need to omit that term, you can use that result to plug it there and omit, right? Now, since I'm seeking v2, we need v2, which means v1 is unknown. v1 is unknown. Sorry, v1 is unwanted. Sorry, unwanted. v1 is unwanted, right? Subject that unwanted term from this. v1 equals a v2 over capital A. So keep it here. I will keep it here as 1 and going to apply Bernoulli's theorem now. To use Bernoulli's equation, you have to have a streamline. Now again, I'll be choosing the same streamline which goes through x and y, right? I'll be choosing the same streamline which goes through x and y. Look at here. For a streamline goes through x and y, right? Now, if we use Bernoulli's theorem here, px plus half rho v1 squared plus, there's no rho gh term because my point x is at zero level, so no rho gh, no h, that is why there's no rho gh. And here py plus half rho v2 squared plus 0 at y also, that is on the same streamline I considered, that's at zero level, so there's no potential energy. Now, px and py are given, we need v2, v1 is unwanted, so therefore I'm going to plug that. So before plugging, let me simplify this a bit. Px minus py can be written as half rho times v2 squared minus v1 squared. Now, to remove v1, I'm going to use this, right? Px minus py equals half rho, this can be written as v2 squared minus, for v1 that is a v2 over n, so v1 squared can be written as a squared v2 squared over capital A squared. Now v2 squared is also common, I'll be taking it out. Px minus py equals half rho v2 squared and brackets 1 minus simple A squared over capital A squared, right? We can put a common denominator there. Px minus py equals half rho v2 squared, common denominator is capital A squared, and this will be capital A squared minus simple A squared, right? Now from this, subject v2 squared, let me write it here, subject v2 squared will be, you can cross multiply this 2 to the left hand side, 2 times px minus py over rho capital A squared minus simple A squared over A squared. Cross multiplication. This is v2 squared, we need v2, consider the square root. So v2 will be square root of A squared can be taken out as A, and root, this remains inside the root, 2 times px minus py over rho times capital A squared minus simple A squared. This is the final answer. So likewise, if you need to connect, if you need to combine area into calculation, the only way is using continuity equation. And as I told you, as a habit, always subject the unwanted term from continuity equation and plug it in Bernoulli's equation when you need to remove that particular term, right? So that is how these questions are done. When you do 3-4 questions, you will see like some similarities among questions, right? So that is one thing you should know, right? Take it down, and if there are any questions, forward them through the live chat. right? If you have any questions, don't hesitate to ask. You can always ask your questions and get it clarified. You can always ask your questions and get it clarified. Right. Now, if you are facing A levels this year, 25 batch again, go through these parts again and again, because there's a possibility of coming a Bernoulli's question this year as mechanics, right? So therefore, if anyone from 25 batch is watching this live, pay some attention to Bernoulli's theorem this year, right? Right. Okay, let's move on to the next question. Question 3. And below this question, write down. Use continuity equation. Use continuity equation and subject unwanted term. 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 From there, to use in Bernoulli's equation. From there to use in Bernoulli's equation. Right. Question 3. A container of cross-sectional area capital A has a small hole of cross-sectional area simple A in its bottom. Determine the speed of liquid column flow at hole when vertical height of the liquid column is h. Right. It should be marked up to the liquid level. That's a small typing mistake, printing mistake in the tut. Right. So I'll be drawing it anyway. Question 3. The tank is like this. And here there's a small hole. Right. And the liquid level is up to some level, and up to that level the height is h. And cross-sectional area of the container is A. So which means this cross-sectional area of the container is A, and here cross-sectional area of this hole is simple A. Right? And we need the speed of the liquid at hole. We need the speed of the liquid at hole. Right? Look at here. Now again, you need to select a streamline first, because if you have to apply Bernoulli's theorem, you have to have a streamline. So I have clearly said you that if we are to apply Bernoulli's theorem, you have to have a streamline. There are infinite number of streamlines which are coming from this top surface to this hole, because when liquid goes out, all the liquid particles here are coming through different streamlines, and all of them are coming to the hole and going out from the hole, right? So therefore there are infinite number of streamlines here, so you can choose any streamline, that doesn't matter. You can choose any streamline. So I'll be choosing this kind of a random streamline, right? For my clarity, I'll be labeling this as point P and point Q. I'll be labeling it as point P and point Q. Streamline එක mark කරානම් ඊට පස්සේ earth zero level එක mark කරන්න, because you have to apply Bernoulli's theorem, right? Considering lowest level as earth zero level is easier, so therefore I'll consider lowest level as earth zero level, this level as earth zero level, right? And let's mark these velocities as v2 and v1. Let's mark these velocities as v2 and v1, and what we are seeking is v2 again. Velocity through the hole, what we are seeking is v2. v2 එක හොයාගත්තා නම් වැඩේ ඉවරයි. හරිනේ? I told you, if areas are given, that is very straightforward. Use continuity equation first. So first I'm going to use continuity equation, right? Using continuity equation, a1 v1 equals a2 v2, then for here capital A v1 equals simple A v2. Since we need v2, unwanted term is v1, I'll be subjecting v1 again. So a v2 over capital A, and we'll be considering it as 1. Right? And to apply Bernoulli, you have to have a streamline. Now my streamline is PQ. My selected streamline is PQ. My selected streamline is PQ. Then using for streamline goes through P and Q. You can use any labels to you can give any labels to these points, right? Now, if there is already given as x and y as in the previous questions, you can stick to the given labeling. But if any labeling is not given, you can introduce your own labeling and mark it in the diagram and introduce it here, right? For streamline goes through P and Q, right? Which means these terms are equal at P and Q. This is not a mandatory line to write. This is for your reference. This is for your reference. Otherwise, that's not a mandatory line to write. Okay, pressure. Now, if any surface is open to atmosphere, if any surface is open to atmosphere, it undergoes atmospheric pressure, or it experiences atmospheric pressure, right? Repeating again, if there's any point which is open to atmosphere, it has, or it experiences, it feels the atmospheric pressure, right? So when we are standing on atmosphere, now each and every point in my body feels atmospheric pressure. There's no direction for pressure because pressure is a scalar. Then from all directions, from all around directions, my body has, now we have infinite number of points in the body. If we consider it as points, for all points, at all points, I have atmospheric pressure. So therefore, like always, if there's anyone which is open to atmosphere, any surface which is open to atmosphere in a liquid, it feels atmospheric pressure. Now this top surface is open to atmosphere, and this hole is also open to atmosphere, right? So they gave atmospheric pressure again. I'll be marking atmospheric pressure as P naught. And at this hole also, there is at the atmosphere. Let me label it here. So that is at the atmosphere. So it has atmospheric pressure, right? And let me put my Q here. Okay. Okay. Then substitution is like this. Then pressure at P is P naught, atmospheric pressure, plus half rho V1 squared, plus now earth zero level is at here, my point P is at here, then rho GH exists, rho GH is non-zero, right? In rho GH, H is the vertical height from earth zero level to considered point, right? Because it comes from MGH, it breaks down from MGH. In MGH, you know, H is vertical height from earth zero level to center of gravity of object, right? So when we consider particles, center of gravity of the object will be at the same point because that's a particle. So therefore, in rho gh also H has the same meaning. In rho gh also H has the same meaning. So that's the vertical height from earth zero level to center of gravity of the object. Now in this case, since we are considering particles, that's the vertical height from earth zero level to that considered point. So that is rho gh here. Rho gh equals, other side, Q is also open to atmosphere, which means P naught, pressure is P naught, and half rho V2 squared plus, this is at earth zero level, so there's no H. Kinetic energy, potential energy per unit volume is 0. Rho gh is 0. Right? Simplify this. Simplify this. P naught to P naught cancels. P naught to P naught cancels. And if I subject rho gh equals half rho V2 squared minus V1 squared. Now I need V2 has to omit V1. To omit V1, I have this substitution here. Right? Cross multiply this 2 to other side. 2 rho gh equals rho here V2 squared minus, instead of V1, you can write this A squared V2 squared over capital A squared. Right, now rho also cancels. Rho also cancels. Which means 2gh equals, you can take V2 squared out, 1 minus A squared over capital A squared. 2gh equals V2 squared. This is capital A squared minus simple A squared over capital A squared. So V2 squared is, you can cross multiply and subject V2 squared 2gh A squared over capital A squared minus simple A squared. 2gh A squared over capital A squared minus simple A squared. This V2 squared, you need V2. You need V2. So V2 is square root of A squared is capital A. So A root 2gh over capital A squared minus simple A squared. Final answer. Right? Take it down. Take it down. If there are any questions, you can forward, you can ask. If you finish question 3, you can go to question 4 and try it out before the discussion. Right? If you have already finished question 3, go to question 4 and try it. Right? If you have already finished question 3, go to question 4 and try it. So likewise, you can keep trying more questions, and then when I'm discussing, you can listen to the discussion. Question 4. Question 4. Question 4. Okay. Question 4. A massive water tank is filled with a liquid up to level H. Right? It has a tiny hole in its bottom. Determine the velocity of liquid spills out from the hole. Right? And there's a typing mistake again. In question 4, areas are not given. Right? Make that correction. In question 4, areas are not given. Erase that capital A and simple A marked in the diagram. Right? That is not given. No? That is not given. In question 4, areas are not given. Right? Erase that and come to the question. Erase that and come to the question. Right? Here, the logic is this. Listen. Logic is this. If you are given massive tanks with very small holes, tiny holes, right? Very large tanks with small holes. So we know when from a small hole, when the liquid goes out, we don't see any velocity or any speed at the topmost point, at the top level of the surface, right? Now, as an example, let's assume from a very large tank, it has a small hole like a needle. Needle එකක් වගේ පොඩි hole එකක් තියෙනවා ලොකු tank එකක. ඒතර දැන් ඒ needle එකෙන් liquid එක එළියට යනවා. එළියට ගියාට අපිට considerable විදියට significant විදියට මේ උඩ water level එක drop වෙන්නේ නැහැ. Right? So we don't see a significant drop in water level, top water level, even when the liquid goes out, if that's a tiny hole, if that's a very small hole. So therefore, in such kind of cases, we can neglect the velocity here. We can neglect the velocity at top surface. So therefore, we can neglect that velocity. Right? Okay. So no need to continue the equation now. Areas are not given. We can directly use Bernoulli's theorem. Right? Using Bernoulli's theorem, see, for streamline goes through P and Q. Right? At P, as atmospheric pressure P naught, and there is no rho gh because we can consider this velocity as 0 now. You can consider this velocity as 0 now. Right? So therefore, no kinetic energy. But rho gh is there, and at the hole also that is open to atmosphere P naught. Plus there will be a velocity, so half rho v squared exists, but that is at a 0 level. Rho gh is 0. Right? P naught to P naught cancels. Rho gh equals half rho v squared. Rho to rho also cancels. V squared equals 2gh. V equals root 2gh. So final answer here, V equals root 2gh. V equals root 2gh. Right? Take it down quickly. Take it down quickly. Right? Okay, below the question, write down. Below the question, write down with a red pen. You would have mentioned this with a red pen. After the question, write down if very small holes are given with massive tanks. if very small holes are given with massive tanks, if very small holes are given with massive tanks, neglect velocity of liquid at top surface. Neglect velocity of liquid at top surface. Neglect velocity of liquid at top surface. Right? Neglect velocity of liquid at top surface. Right? Okay. Let's move on. Question 5, page number 3. Question 5. Page 3, question 5. Okay. Setup is given. Right. Okay, it says a liquid of density rho flows through a Venturi tube as shown. It should be a Venturi tube, not a Venturi. It should be Venturi tube. This is called a Venturi tube. Venturi tube is used to measure speeds of a liquid. Measure speed of a liquid. Venturi tube is used. There are different types of Venturi tubes. The one I have given in the next question is also Venturi tube. There are different types. This is called a Venturi tube. Venturi tube. This is called a Venturi tube. Venturi tube. Right. Density rho flows through a Venturi tube as shown. Vertical heights of liquid columns at vertical tubes measured from X and Y are simple H and capital H. Capital H is greater than simple H. Cross-sectional areas of wide and narrow sections of tube are capital A and simple A. Right. These points are given as X and Y. This is X. This is Y. Right. And areas are capital A and simple A. Areas are capital A and simple A. Consider atmospheric pressure as P naught. Okay. Now these two tubes are open to atmosphere from the top. These two tubes are open to atmosphere. Right. First one, mark positions of liquid columns in vertical tubes and label them properly. Mark positions of liquid columns in vertical tubes. These are the vertical tubes. Right. Okay. Now, when the liquid flows from here to here, right? When a liquid flows from here to here, like this, when the liquid flows, now, before also I gave you, this is the relationship it follows. P is proportional to area, inverse proportional to velocity. This is what it follows. So therefore, higher area means higher pressure. Higher area and higher pressure. Higher pressure means now liquid in these vertical tubes are static. Only the liquid in the horizontal tube moves. Right? In the Venturi tube, the liquid in horizontal tube moves. And some part of that same liquid goes to the vertical tubes. But in vertical tubes, there is no movement for the liquid. In vertical tube, there is no movement. There is just resting at the vertical tube. Right? So therefore, now we know higher area means higher pressure. Then if I write vertical pressure, if I write pressure from this vertical tube here, vertical liquid column here, so you all know that hydrostatic pressure is H rho g. Then to represent a higher H, there should be a higher pressure, there should be a higher height, higher H, because pressure is H rho g. And we know pressure is H rho g, which means higher pressure means higher H. Higher pressure means higher H. Now from this we know From this we can say Px is greater than Py. Px is greater than Py, which means now combining to this, then height at x should be greater than height at y. Right? Height at x is given. That's the higher height, capital H. Capital H is greater than simple H. It's a given data. It's given, na? Then you have to mark it properly. Right? Capital H is greater. Then it should be something like this. Right? Then from here, this height is capital H. And this is simple H. It should be lesser than capital H. And it is somewhere here, simple H. This is how it should be marked. Right? That is how it should be marked. Right? That is how it should be marked. Okay, then what's the next question? 1. Mark positions of liquid. Right, that is done. 2. Write down pressure at x. So you can write pressure at x using atmospheric pressure. Atmospheric pressure is given. This is open to atmosphere P0. This end is also open to atmosphere P0. Right. So question 1 is done. Then part 2. Write down pressure at x. So we can write Px as P0 plus capital H rho g. Right. Then write down pressure at y. 3. It can be written as, let's say, Py, P0 plus simple H rho g. By considering speed of liquid at point x and y as Vx and Vy, obtain a relationship among capital A, simple A, Vx and Vy. So which means you have to apply continuity equation. Apply continuity equation. Part 4. Part 4. Using continuity equation. A1 V1 equals A2 V2. Right? A1 V1 equals A2 V2, and these velocities are given as Vx and Vy. So we can consider this as Vx and Vy. Consider these velocities as Vx and velocity here as Vy. Right? Then using continuity equation, then capital A Vx equals simple A Vy. Relationship among these terms. So this is the relationship. Just the relationship is needed. 5. By using it or any other method, find speed of liquid at narrow section Vy. At narrow section, we need Vy. Okay, if Vy is needed, we can subject Vx from here. Since Vy is needed, subject Vx from here, Vx will be A Vy over capital A. Right? I'll be considering it as 1. A Vy over capital X, capital A. I'll be considering it as 1. Then I'm going to use Bernoulli's theorem for the streamline which goes through X and Y. Right? For streamline goes through X and Y. For streamline goes through X and Y. Right? Then at once we can apply it as Px plus half rho Vx squared plus there's no rho g term, and Py plus half rho Vy squared plus there's no rho g term here as well, because I'll be considering this as my earth zero level. Both points are at earth zero level. Both points are at earth zero level. Right? Then we need Vy. We have 2 answers for Px and Py here. We have already got 2 answers for Px and Py here. So we can plug that there and simplify. We can keep simplifying after plugging these values. See? Px can be plugged as P0 plus capital H rho g plus this is half rho Vx squared. And right hand side Py is P0 plus simple H rho g plus this is half rho Vy squared. P0 to P0 cancels. Right? Then I'll be taking rho g out while taking this term to left hand side. So rho g h minus h, and from the other side at once we can take half rho out. When half rho is out, vy squared minus vx squared. For vx we have an answer here, right? Cross multiply this 2, then 2 rho g times capital H minus simple h equals rho times rho cancels, vy squared minus vx is a squared vy squared over capital A squared. Rho cancels. Rho cancels. Right? Okay, then subject this 2g h minus h equals, we can take vy also out, vy squared out, then apply a common denominator inside, then 2g h minus h equals vy squared, common denominator is a squared, here capital A squared minus simple A squared, right? Then vy squared will be, vy squared is 2ga squared capital H minus simple h over capital A squared minus simple A squared. This is vy squared. We need vy. So therefore vy is the square root of capital A squared is a, then a root 2g capital H minus simple h over capital A squared minus simple A squared. Final answer. So this is a good question. Right? This is a good question with few thinkings, right? About riding pressures. Riding pressures, you have something to think, you have a thinking, and you have to properly simplify it by plugging these values. That's a good question, right? That's a good question. So slightly we are moving towards advanced questions, right? Gradually we are moving towards advanced questions. So this is a good one. Take it down. And can ask if there are any questions, Can ask if there are any questions. Right. Is it all clear up to this point, students? Right? Thumbs up එකක් හරි දාන්න බා. Live එකේ ඉන්න කට්ටිය at least thumbs up or say it's clear. Up to this point, is it clear? කොහොමද questions ටික මෙතෙන් යනකම් clearද? තව ඉස්සරහට අපිට advanced questions තියෙන advanced types and different types are there. Right? Okay. All good? Any questions? Okay, let's move on. Now, even though the liquid flows horizontally, listen, even though the liquid flows horizontally, we can write h rho g vertically because horizontal velocity, horizontal vector is not going to affect our vertical movement of h rho g, right? For h rho g, we need a vertical movement. For that vertical movement, horizontal velocity doesn't matter because that's a perpendicular vector for that direction, right? Mention this below with a red pen. Mention this below with a red pen. Mention this below the question. H rho g can be used. H rho g can be used. H rho g can be used to write pressure difference. H rho g can be used to write pressure difference. H rho g can be used to write pressure difference vertically, even when the liquid flows horizontally. Even when the liquid flows horizontally. Even when the liquid flows horizontally. Since there's no impact from perpendicular vectors. 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 Right. Next one. Okay, next one is also a good question. Question 6. That's going to be a good question. Good one. Right. So if you have tried before me, that's very good. Now you can check your answers with mine. Right. For 25 students who are taking A levels in 25, now this is the 12th week going before the exam. Right. Next week will be the 11th week, and in terms of days, I think it's 94 days before the exam. Right. With today, that is 94 days. Right. Now today is almost gone. Now what's the time? 9:30, 9:34. Right. Now 93 days to the exam. Right. So work hard. Work hard. And if you are a 26 one or maybe 27, ඔනකට මේ live එක බලන්න පුළුවන්. 26 නම් so work hard because you have around an year ahead, right? So there is a lot to do. There is a lot to do, right? So more than a year actually, and 2 months වගේ තියෙනවා 26 නම්. So there's a lot to do. So keep your momentum of work and study hard, work hard to achieve that goal. This is a doable thing, right? As long as you work hard, this is very much doable, right? අනිවාර්යෙන් කරන්න පුළුවන් වැඩක්. Okay, 6. A liquid of density rho flows through a venturi tube. Cross-sectional areas of venturi tube are capital A and simple a. Capital A is greater than simple a, respectively. Density of manometer liquid is D. Manometer කියලා කියන්නේ ඔය පහළ තියෙන YouTube එක වගේ කෑල්ල. Right? Manometer. That is called the manometer. Right? Liquid is D. If difference between liquid columns in manometer is H, determine velocity of liquid at narrow section of tube. Determine velocity of liquid at narrow section of tube. Right. Okay. Narrow section එක diagram එක නම් එච්චර පේන්නේ නැහැ. Consider capital A as greater, right? So consider capital A greater than simple a, right? Consider that as a given data. Capital A is greater than simple a, right? Now this is the tube. Ah, yeah, that is marked, ne? Ah, no problem. Simple A is marked in the diagram. That is marked. With the dotted line, simple A is marked. So that is where the simple A is. Right? Okay. Okay. Flow directions are given and 2 points. Are there 2 points given? No. No 2 points given. So we are going to introduce points. I'll be considering 2 points on the same line. One here, let's say X, and the other point here, let's say Y. Right? And liquid flow directions are given like this. Flow directions are given. And about the manometer liquid, the difference in heights of the manometer liquid is H. So this is H. Right, and density of the manometer liquid is D. Right, density here is rho. Okay. Capital A and simple A. This area is capital A and this small area is simple A. This is capital A. Right. Determine velocity of liquid at narrow section of tube V. Okay. So let me mark this as that is given as V2. So let's consider it as V2. And let's consider this as V1. Okay. We need the velocity at narrow section. Okay. Now it is like this. Now this part of the tube is filled with the liquid of rho, liquid of density rho. This part is filled, and some part of that liquid is also coming into the manometer like this. Some part of that liquid is also coming into the manometer. Right? It's coming into manometer like this. So this is how the liquid is. Right? So that is how the liquid is. Okay. Now areas are given. So first I'm going to apply continuity equation. Using continuity equation. Then capital A V1, A1 V1 equals A2 V2. That's capital A. Capital A V1 equals simple A V2. Since we need the narrow section, V2 ne V1 subject karanna. Unwanted term mein subject karanna. So I'll consider this as 1. Right. Now, before writing pressure differences, before applying Bernoulli's theorem, and before writing pressure differences in Bernoulli's equation, right, I'm going to get the relationship between these pressures using the manometer. Look at here. Now, this is the difference in this question. Right, this is a good question with a difference. Right, the difference is now the manometer is given and you are given the density of the liquid at manometer. Right. See, let's assume height from here to here as, right? Let's assume height from here to here as, let's assume this as X. We don't know what that is. Let's assume that as X, right? Let's assume. And then I'm going to write pressures from X to Y starting from this point. Hydrostatics. So using hydrostatics, you can write pressure starting from X. See, I'll be writing it here. Look at here. Starting from X, you can write these pressures, Px, and you can come down, right? Coming down a height X plus H with the liquid rho, then plus H rho G, H is X plus H rho G. Now we are here, right? Pressures at same level of the same liquid is same, which means this pressure is also same. Now you can go up minus H, but density is D now. It's dG. Now we are here, and again up minus X. May height difference X X rho G, which means now you add Py. And with the areas, you know, Px is greater than Py, yeah. Capital A is greater than simple A, which means Px is greater than Py. Px is greater than Py. Right? Now simplify this and subject this Px minus Py. See, if you simplify this, Px plus x rho g plus h rho g minus hdg minus x rho g equals Py. Right? You can see x rho g2 minus x rho g cancels. X is actually put by me, so it should cancel. So it cancels. Right? So Px minus Py, you can subject Px minus Py. Px minus Py because Px is greater. If I subject Px minus Py, other side will be hdg minus h rho g. Right? So you can take hg out. Px minus Py, h and g are common. So d minus rho. I will consider this as equation 2. Right? Writing pressures. Writing pressures. Now only I'm going to apply Bernoulli's theorem. Now only I'm going to apply Bernoulli's theorem. Right? Now let's apply Bernoulli's theorem. I have this streamline which goes through x and y. For streamline goes through x and y. For streamline goes through x and y. Right? Then pressure at x is Px plus half rho V1 squared. Rho GH is 0 because I'll be considering this as my earth 0 level. This is my earth 0 level. Right? And y Py plus half rho V2 squared plus 0. Right? Now I'm going to create Px minus Py. Px minus Py is half rho V2 squared minus V1 squared. Now for Px minus Py, I have got an answer here. For Px minus Py, I have an answer here. Plug that here. That is Hg d minus rho equals half rho V2 squared minus, for V1 squared, I have here simple A squared, V2 squared over capital A squared. Right. Cross multiplication 2Hg. Right. Cross multiplication 2Hg d minus rho equals rho times. You can take V2 squared out. Then this will be capital A squared minus simple A squared over capital A squared. Subject V2 squared will be 2HGA squared brackets d minus rho over rho times capital A squared minus simple A squared. Right? And if we need V2 is the square root. Now, when the square root is considered, A squared will be coming out as A, and root 2GH d minus rho over rho times capital A squared minus simple A squared. This is the final answer. So this is again another good question, a very good question with the thinking. You have to think out of the box to get this relationship among pressures or between pressures and plug it here. Right? On the question එකක් මේක fluid dynamics වලින් කරන්න පුළුවන්. Right? Take it down, and if you have any questions, put them to the live chat. right? Okay, students, any questions up to this point from what we have discussed? Any questions or is it clear? Live එකේ ඉන්න කට්ටිය දාන්න බලන්න message මේ chat එකට දාන්න. Is it clear? I need a response before moving on. Now we are moving towards the other types of questions now, right? So what do you say? Is it clear enough, students? What do you say? Okay, right? This part is very important. And make a different part. This part is very important, right? So I wrote pressures along the manometer from Px to Py, right? From x to y, right? I wrote pressures along the manometer using H rho g terms and got something for pressure difference between x and y, right? So that's one different thing we did in this question. Right? Okay, let's move on. This is also a type of a Venturi tube. I told you there are different types of Venturi tubes. So this is also a type of Venturi tube we have, Venturi tubes we have. And as I told you before, Venturi tubes are used to measure speed of a liquid. Measure speed or velocity of a liquid. Venturi tubes are used. Next. Question 7. A student tries to make a paper of mass M and cross-sectional area A by blowing an airflow above the paper sheet. There's one part missing in the question. The student tries to it should be a student tries to keep a paper in equilibrium. It should be, please correct that, question 7. I'm referring to question 7. Right, in question 7, there's a mistake. In question 7, there's a mistake. It should be corrected as a student tries to student tries to keep a paper in equilibrium. A student tries to keep a paper in equilibrium. A student tries to keep. A student tries to keep a paper in equilibrium. A student tries to keep a paper in equilibrium of mass M and cross-sectional area A by blowing an airflow above the paper sheet. If density of air is rho, what's the minimum speed of blowing airflow? What's the minimum speed of blowing airflow? Right. Okay, now here onwards we have a small difference. Here onwards you have a small difference. Difference is this. Now so far we discussed the questions from liquids. अब liquids questions ने कथा करें. So far we discussed the questions from liquids. Now here we are going to discuss questions from air mediums, gaseous mediums, because this is fluid dynamics. I told you at the beginning. Here we can do, this is applicable, this is valid for both liquids and gases, right? And all first six questions were from liquids, and from question 7 onwards, 7, 8 and 7, 8, 9 I guess are from gases, gas mediums, right? Now when you are using for gas mediums, we do something like this. Sorry. We do something like this. Listen first. When we are using Bernoulli's equation for gaseous mediums, gases in the sense gas mediums, we do something like this. Look at here. First thing, in gas mediums, we don't consider OGH. The reason is rho of a gas is very less. Now, in reality, rho of gas is like 1.2, a very small value. So therefore, rho GH term is neglected in gas mediums, right? In gas mediums, first point is rho GH is neglected in gas mediums. Rho GH is neglected in gas mediums because that is very small. Rho GH is neglected. Rho GH is neglected in gas mediums, right? And the next idea is when we apply Bernoulli's theorem for two points which are in opposite directions of something like this. See, let's say I need to apply for point A and B. I need to apply Bernoulli's theorem for point A and B. When an airflow is flown like this, when an airflow is flown like this, see, say we need to apply Bernoulli's theorem for A and B. Now in such cases, what we do is, we don't have a streamline which goes through A and B. Therefore, we have to select a third point that is far away from this setup. Far away, right? We'll be marking it somewhere here, and that's a far point, a far away point. And where we will consider this velocity of this blow is 0. Then actually what we are doing is this. Now, if I consider this streamline, now if it is becoming 0, now at some point it will be 0 like this way, right? So let me draw it again nicely. See, speed of this will become 0 at some point. This one also will become 0 at some point. So there we will be considering a third point as C when velocity is 0. Right? Now, since we don't have streamlines which goes through A and B, what we do is we are using Bernoulli's theorem for A and C and B and C separately. Right? So we can do this. We can use Bernoulli for A and C, same streamline, and for B and C also. Right? B and C also. And since this is equal, which means A and B are equal. Which means A and B are equal. We are going to use that idea. We are going to carry that idea forward when using for these kind of scenarios. Therefore, when we mention that, we are mentioning that as by using Bernoulli's theorem for A and B separately. Separately for A and B separately, because there's no streamline goes through. Now in previous cases we mentioned this streamline. Now we don't have a streamline which goes through A and B. In such cases, this is what we do, right? You can take down a note if needed. Right? You can take down a note if needed. Right? Now let's move on to the given question with that idea in mind. Okay, now we are in question 7. Okay, this student tries to blow this. See? හරි මට චිත්‍රය දෙන්න තේරෙන්නේ නැහැ හරිනේ. So this is the sheet. This is the sheet. And the airflow is like this. Airflow is like this. This is the airflow. So let's assume velocity of this airflow as v here. Right. And make a pair of mass m. So weight here is mg. Weight here is mg and area is given a and density of air is rho. Area a. That's all. Right. Look at here. Look at here. Right. Now, if you haven't tried this, if you haven't tried this before, give me a second to check whether I can show it to you. Yeah, I have paper. See. So this is what this person, this student is trying to do. Right. Now he has a paper like this and he is trying to blow an airflow from the top. Now what happens when an airflow is blown from the top is when velocity increases air rest in when I blow velocity of air increases. When velocity increases, you know, pressure decreases because this is the relationship. Relationship is pressure and area and velocity. This is the relationship, right? So therefore what happens is when velocity increases, pressure decreases. When pressure decreases, the force exerts here from high pressure to low pressure because this paper below the paper we have rest in air, velocity is 0, rest in air, and above the paper when I blow velocity increases, so pressure decreases. From high pressure to low pressure the force exerts. Now from that force this mg of the paper will be balanced and this can be kept in equilibrium. This can be kept in equilibrium. So this is what is going to be done by this student, right? Something like this. මේ paper එක මෙහෙම තියාගෙන උඩින් airflow එකක් දානවා. Can you see? There's no magic here. මෙතන මේ මොකද හොරයක් නැහැ, magic එකක් නැහැ. Velocity එකක් උඩට දුන්නු ගමන් when velocity increases, pressure decreases. Always a force created if there's a pressure difference from high pressure to low pressure. Pressure difference එකක් තියෙනවා, force එකක් තියෙනවා because pressure is F over A නේ. F is PA. Right? Pressure difference එකක් ආපු ගමන් force එකක් එනවා. ඉතින් ඒ force එක උඩට ආපු ගමන් vertically upwards force එක ආපු ගමන් මෙයාගේ mg එක එකෙන් balance වෙනවා. ඒකයි මේක උඩට එන්නේ. Right? You can see it? Right. ඕක තමයි මේ ගානේ කරන්නේ. ඕක තමයි මේ ගානේ කරන්නේ. බලන්න. I hope it is clear. I hope it is clear. Right. Right. Now, let's consider 2 points here as like this. Let's consider one point here as x and another point below the paper as y. Now, like this, I'm going to apply Bernoulli's theorem for x and y separately. Right? I'm going to apply Bernoulli's theorem for x and y separately. See? Using Bernoulli's theorem for x and y separately. For x and y separately, right? We can write this at once, but we are using separately. Yeah? And this is pressure at x, px, pressure at x, right? Plus half rho v squared plus 0 because we will be always neglecting rho gh when we are dealing in gas mediums, right? This is py plus there's no velocity here. Velocity this is the rest in air. This is rest in air. So velocity at this air is 0. 0 plus 0. Right? We know higher pressure is at y because you know this. මේ මම කලිනුත් ලියුවා මම erase කරා pressure to area to velocity. This is the relationship, right? So when velocity is higher, pressure is lower. When velocity is higher, pressure is lower. Higher the velocity, lower the pressure, right? Higher the velocity, lower the pressure. Then higher pressure, higher velocity එකකින් උඩනේ, right? Higher velocity is at the top layer, above the paper. Then that is the lower pressure. එහෙනම් higher pressure එකේ තියෙන y වලට py minus px. So I'm going to subject this py minus px pressure difference now equals half rho v squared. Pressure difference equals half rho v squared. I'll be considering this as equation 1. Now, to make this paper in equilibrium, we need a vertical equilibrium because that is in an equilibrium. So let's assume the force exerts by pressure difference as F. Let's assume the force exerts by pressure difference on this paper. Force exerts on this paper by pressure difference as F, right? Then, by considering vertical equilibrium, see, now what you can do is you can consider the vertical equilibrium. Vertical equilibrium by considering vertical equilibrium. Vertical equilibrium. Vertically upwards forces equals vertical downward forces. Vertically upwards I have F, downwards mg, right? But we know F can be written as delta PA because pressure is, or pressure difference is force over area. Pressure kila force over area. Then force is pressure into area. Pressure is pressure difference now. Pressure difference Py minus Px, right? Then pressure difference here is Py minus Px. Area is given as A equals mg. Py minus Px can be substituted by half rho v squared equals mg. We need v, so v squared is 2mg over half rho v squared A, 2mg over 2mg over A rho. V is square root of 2mg over A rho. That is the final answer. So this is the first experience you got about gas mediums. So first thing is in gas mediums we neglect rho GH, and the second thing, that is what I explained before. Since if you don't have streamlines, what we do is actually what we are doing is considering a third point and applying separately and getting it done. Now here, therefore, we have to mention that by using for these points separately, not a streamline. right? Streamlines දෙකක් තියෙනවා මම කලින් කරලා පෙන්නනවා. ඒක මිස් වුණා නම් වීඩියෝ එකේ කලින් පෙරට ගිහිල්ලා බලන්න. වීඩියෝ එකේ මුලට ගිහිල්ලා බලන්න. ඒක තමයි එක්ස්ප්ලেইন කරේ. Streamlines දෙකක් consider කරලා ඒ දෙකේ result එක අරගෙන combine කරලා තමයි මේක ගත්තේ. When you are applying it, you can apply it at once like this. Take it down, and if there's any questions, forward them to the live chat. Right, take it down. right? Mention this below the question. Mention this below the question. Mention this point below the question with a red pen. Potential energy per unit volume. Potential energy per unit volume. Potential energy per unit volume within brackets rho gh. Rho gh is neglected in gaseous mediums. Is neglected in gaseous mediums. Potential energy per unit volume within brackets rho gh is neglected in gaseous mediums, right? Is neglected in gaseous mediums. Okay, let's move on. Let's move on. Question 8. Go to question 8 and see whether it's doable. Okay, let's see. Question 7. Sorry, 8. Question 8. An aeroplane has two wings. A cross section of a wing is shown in the figure. Speed of air flows above and below wing is 60 ms minus and 40 ms minus 1 respectively. Net area of aeroplane is 8 square meters and mass of aeroplane is 1200 kilograms. Density of air is 2 kgm minus 2. Area of a wing is 4 square meters, right? Okay. Determine the pressure difference across a wing, right? මේ තියෙන wing එකේ cross section එකක්. This is like this. If you don't know, now this is the aeroplane. See, to explain this a bit, now this is an aeroplane, and wings are like this. Wings are like this. Now, if I take a cross section of this wing, a cross section, that cross section look like this. This is called a streamline shape. This is called a streamline shape, right? This is called a streamline shape. Streamline shape. ඕලෙවල්ස් වල එහෙමත් ඕක අහලා ඇති. ඔය බර්ඩ්ස් ලාගේ එහෙමත් තියෙනවා කියලා උගන්වනවා නේද? අර කියන්නේ streamline shape එක බර්ඩ්ස් ලාගෙත් තියෙනවා කියලා ඒගොල්ලන්ට easily. මේ බර්ඩ් කෙනෙක් වුණත් fly කරන්නේ මේ බර්න්ලිස් theorem එකෙන්. right? බර්න්ලිස් theorem use කරලා තමයි මේ මෙහෙම flow වෙලා යන්නේ. ඒතර යාට streamline shape එකක් තියෙන. aeroplane also that's the same streamline shape. right? එන්න මේක තමයි දීලා තියෙන්නේ. cross section එක තමයි දීලා තියෙන්නේ. This is the cross section. right? මෙතන තියෙන cross section එක තමයි මේ දීලා තියෙන්නේ. cross section this one. This cross section is given. right? Alright? Now let's see. Let's see. Okay, this cross section is given now. (40 ms minus 1) and this is 60 ms minus 1. This is the cross section of this air wing. Cross section. Okay. First one, determine the pressure difference across a wing. Right. So you know now that if there's a change in speeds, change in velocities, there will be pressure difference. Right. Now, using 2 points, top and bottom of the wing, across the wing, let's use Bernoulli's theorem. Simple as that. Right? Tell me Bernoulli's theorem. See? So I'll be considering this point as point A. Or let's say X. And I'll be considering this as Y. X and Y. Right? Now, first one, we can use Bernoulli's theorem using Bernoulli's theorem. For point x and y, for points x and y separately, x and y separately, right? Now, which means x equals y, right? So let's say pressure at x is px plus half rho v squared, half rho vx squared, no rho gh in air, right? Py plus this is half rho vy squared plus no rho gh in air, right? Now you know higher velocity means same thing again, pressure to area to velocity is like this. So higher velocity means low pressure. So low pressure is at y. So I'm going to subject px minus py. We need pressure difference. Px minus py is half rho vy squared minus vx squared. Plug given values and simplify. Px minus py equals half rho is 2. Rho is 2 given vy 60 squared minus vx 40 squared, right? So don't find the square of 60 and square of 40, right? Make questions la me wage type එක හැම වෙලේම එනවා. So in such cases don't find these squares. You can apply the difference of two squares. දන්නවනේ ඕලෙල්ස් වලදී difference of two squares. මෙතනට ඔයාලට ලියන්න පුළුවන් මේක. You know a squared minus b squared can be written as a minus b, a plus b, right? So same thing applies here. Which means this 2 to half cancels. Then px minus py equals, this can be written as 60 plus 40 times 60 minus 40, right? Which means px minus py equals 60 plus 40 කියන්නේ 100 times 60 minus 40 කියන්නේ 20, which means this is 2000. This is a pressure difference in pascals. That is coming in pascals, so you can use nm minus 2. Anything is fine. Pascals or nm minus 2. Right? This is a simplification. So first one, pressure difference is 200 pascals. 2000 pascals. Determine force generates upwards on a wing. Second one, force generates upwards on a wing. So we know, let me do it here. We know force can be written as delta PA, right? Delta P is here. Delta P and px minus py. Px minus py times A. Now px minus py is 2000. And area was given. Area 4. Area is 4. So which means force here is 8,000 newtons. 8,000 newtons. Right. Question 3. What's the direction and resultant force? Direction and resultant force generates on aeroplane. Right. Always the force is asking the resultant force. Resultant force. Then on the aeroplane, it is like this now. It is like this. Are we considering? Yeah, 2 wings. This is only 1 wing. My question එක දීලා තියෙනවා. The aeroplane has 2 wings. Now this is the force on 1 wing. This force is on 1 wing. This is on 1 wing. Right? In aeroplane we have 2 wings. Now the force diagram is like this. There will be 2 Fs on 2 wings. Wings dekhe forces dekai and mg. This is the force diagram. Right? Now the resultant force should be 2F minus mg. Resultant එක upwards with, because මෙතන තියෙනවා 8,000 කියන්නේ 16,000 and I gave you m නේ. m කියන්නේ 1,200 කියන්නේ 12,000. හරිනේ? ඒතකොට 12,000 එකක් එන්නේ. Resultant force. Question 3. Now direction of resultant is, you can clearly see it should be upwards, right? That is upwards. Resultant. resultant force is upwards we have 2F ne. 2F minus mg is the resultant now. 2F කියලා කියන්නේ 2 times this is R 2 times 8000 minus mg කියලා කියන්නේ 12000. So R is this is 16 ne 4000 newtons. So there will be a force 4000 newtons upwards on the plane. A resultant force, or there is an external unbalanced force. There is an external unbalanced force because downwards there is only mg, upwards now 2F. 2F kya 16,000. So the external unbalanced force resulting upwards is 4000 kilograms, 4000 newtons, right? Next, determine acceleration of aeroplane due to above force. If you need acceleration, apply F equals ma upwards. Apply F equals ma upwards. If you need acceleration, 4. Very straightforward. Acceleration එක හොයන්න ඉතින් ගොඩක් equations නෑනේ. You don't have multiple options to find an acceleration, right? So if there is an acceleration, use F equals ma. Then upwards, now resultant upward force is 4000. And m here is 1200 A. Right? Simplify this. These two cancels. A is 40 over 12. A is 40 over 12. By 4 we can divide. By 4 කියලා කියන්නේ this is 10 over 3. So which means acceleration is 3.33 ms minus 2. 3.33 ms minus 2. Then if wing is horizontal, determine the horizontal speed of moving aeroplane. 5. Horizontal speed of moving aeroplane. If the wing is horizontal, this is where you have the horizontal velocity. Because when wing travels forward, the airflow travels with the same velocity backwards. Now this is horizontal, so which means if this is 40, this should also be 40, right? So if that's a straight surface, if that's a linear, if that's a straight surface, velocity of forward and backward airflows will be same. So if the wing travels with velocity v to the right, the airflow travels to the left with the same velocity. Here velocity is different with this streamline shape. Streamline shape එක තිබ්බ හින්දා ඒක different. එහෙම shape එකක් නැත්තම් it's same. Now it's 40. Nothing to find. It'll be 40. Right? 5. 6. If wing is horizontal, okay, that's done. Trace the path of aeroplane when taking off. 6. See? Trace the path of aeroplane. Now for the aeroplane, it has a velocity. See, it has a velocity to the right. Velocities are to right. This is the v. This is v. This is v. Right? That velocity is to right. V එක තමයි 40 කියලා හොයාගත්තේ. Right? That v is 40. And from here we know this acceleration is upwards. This acceleration is upwards. Velocity here and another acceleration upwards. Then it should go in a path which is in between these two. In between these two, something like this. Projectile motion එකක් වගේම තමයි. Projectile motion එකේ වෙන්නේ acceleration එක මෙහෙමනේ. See? මම මේකෙන් පස්සේ explain කරන්න. So this is the path because it has upward accelerations with horizontal velocities. This is the path. This is the path of aeroplane. This is the path. Right? So this is very comparative to projectile motion. In projectile motion, what happens is velocity components are horizontal. Velocity components are horizontal. But when acceleration is vertical downwards, the moving direction is like this. Right? Same idea. In projectile motion, same idea. Velocity එකක් horizontally තිබ්බත්, right? අපි මෙහෙම horizontal projection එකක් දුන්නත් මෙයා එන්නේ මෙහෙම path එකකනේ. Even if I give a velocity horizontally to this, it comes in a parabolic path. Velocity is horizontal, but acceleration is very downward. So it goes in between. Here also same thing, velocity is horizontal, acceleration is upwards, it goes in between. You can take down, and if there are any questions you can ask. From aeroplane, from the swing of the ball, there are popular types of questions are coming. මේ aeroplane එකේ question එකක්. ඊළඟ question එක තියෙන්නේ swing of the ball. Right? Popular questions. Practice these questions and go to the exam. Right? If you are 25 especially, you need to pay some attention here. Right? Take it down, and if there are any questions, if there's anything that you didn't get from this, please forward them to the live chat. Right? Any questions? So is it all clear? No, take it down, take it down, take it down. And if you got any questions, please ask. Right. Okay, any questions? Any questions? No? No questions? All clear? All clear up to this point? Okay. Let's move on then. Right. No questions? Yeah, no questions. Let's move on. All right. Next. Question 9. Question 9 is a model essay question. Question 9 is a model essay question. That's the type of a question that you can expect in the exam. That's the type that you can expect. Right. Let's see. Okay. Let's see. Uh, 9. Okay. A. Write Bernoulli's principle as an equation. Introduce each term correctly. That you know, right? 9. Part A. Write Bernoulli's principle as an equation. P plus half rho V squared plus rho GH equals K, that is a constant. Right? Introduce each term. When you are introducing terms, is pressure at a point. Pressure at point. And half rho V squared, kinetic energy. Kinetic energy per unit volume. And rho GH, potential energy per unit volume. Per unit volume. Right? Then part A1 part A1. Part 2. Mention the requirements that should be fulfilled for the validity of Bernoulli's principle. I told you at the beginning of the class, there are 4 conditions. There are 4 conditions, 4 requirements. The fluid should be incompressible, non-viscous, then steady, and stream. Stream means streamline. Then part B. Okay, it says 2 styles of bowling of a fast bowler are given below. Directing the ball straight away to the batsman without spinning. Then the batsman is tended to protect the wicket. Second one, directing the spinning ball away from the batsman, outswing, or towards the batsman in swing. The objective of this bowling is to compel the batsman to hit the ball and make him be out. Right. A bowler throws a ball of mass 150 grams with a radius of 3.5 centimeters towards the wicket with a horizontal velocity of 30 ms minus 1 in still air having the density 1.3 kgm minus 3, spinning 10 rotations per second. 10 rotations per second. Again, frequency right? Per second value again frequency per second about its vertical axis through the center of the ball. The figure shows the top view of the ball along the spinning axis. Top view. Top view. So 30 is horizontal. Top view is given. Take phi equals 3. What's the direction and magnitude of the velocity of air relative to ball? Direction and magnitude of velocity of air relative to ball. Now, if the ball is traveling at 30 to the left, right, and with respect to that, it should be to the right, opposite and equal velocity. Let me draw it here. Part B. Now, this is given. This is the ball, and this is the seam of the ball. right? And 2 points are given as A and B, right? And rotation direction is given, and 30. Linear velocity is given, 30, right? So if so, now we need the what's the direction and magnitude of the velocity of air, right? Should be backwards. Now, if the ball moves to the right through air, the airflow moves to the backwards to leftwards through air. 30 ms minus 1 leftwards. Question 2. What is the tangential velocity of spinning ball? Tangential velocity of spinning ball. Tangential velocity. So you know frequency of rotation is given. Frequency is given. V equals r omega. And you know how to expand omega. Let me do part 2 here. Part 2. So you all know that V equals r omega. Tangential velocity is V equals r omega. But we know omega can be written as 2 phi f. Frequency is given now. So V equals r, omega is 2 phi f. So V should be, r is given, it was 3.5 centimeters. Radius is 3.5 centimeters. Then 3.5 times centimeter to the minus 2. 2, phi is 3, f is 10. 10 rotations, yeah, 10. Simplify this. 3.5 times 2 is 7. 7 times 3 is 21. 21. 200 again 2.1. 2.1 ms minus 1. Next one. 3 part 1. 3, 1. What is the velocity of layer of air at point A relative to ball? Layer of air. Now, velocity of ball at this point is, see, velocity of ball at this point A is 2. First, you can find them out. See. So let's consider about the ball. If 30 is the linear velocity is acting same at any point. It acting constant at any point. Then at this point of the ball also linear velocity is 30. And at this point of the ball also linear velocity is 30. Right? And tangential velocity is along the tangent. Tangential velocity is along the tangent. Now rotational direction is this. Then along the tangent direction here is this. So that is 2.1. And here along the tangent direction is this. That is 2.1. Now we know the resultant velocity is at these points. At ball. This is on the ball. So you know the velocities of the ball. Velocities of resultant velocities. Values of resultant velocities at these 2 points of the ball. Then if that is on the ball in these directions, on air, it should be to the opposite direction. Right? So let me mark airflow first. Let me mark the airflow first. So it is like this. It will be like this. Right? So this is going to be on the ball. This is on the ball. On ball, what's the value? 30 minus 2.1 can 27.9. 27.9 ms minus 1 to this direction on ball. And this is also on ball. And that value is 32.1 ms minus 1 to this direction. Right? That is on ball. We need on air. What's the velocity of layer of air at point A relative to ball? At point A here. At point A, then it should be opposite. Then at point A, let's say VA is to the left 27.9 ms minus 1. And 2, what's the velocity of layer of air at point B? 2. Let's say VB, right? To the right, so it should be to the left again. To the left. and that is 32.1. Four. Find the pressure difference at either side of the ball at points A and B. Pressure difference. If you need the pressure difference, like before, apply Bernoulli's theorem. Apply Bernoulli's theorem. 4. By using Bernoulli's theorem for points A and B separately. A and B separately, right? So pressure at A, let's say PA. Pressure at A, अभी PA के लगाऊं, right? Pressure at A plus half rho VA squared plus 0. Rho G's term is always 0 in air mediums, gaseous mediums, plus 0. There's an announcement going. I think you also can hear it. It's not going to be cancelled by the noise cancellation, right? An announcement is going. Right, PV plus half rho VB squared plus 0. Plug these values. You know, when velocity is higher, pressure is lower. So pressure at A is lower because higher velocity is at A. So lower pressure is at A. So we need PB minus PA. We need PB minus PA. Then PB minus PA will be half rho VA squared minus VB squared. This is half times rho. Rho was given. 1.3. 1.3. VA is here 27.9. 27.9 squared minus VB 32.1 squared equals PB minus PA. Right. Simplify this as before. I told you 1.3 over 2. These are difference of two squares. Then one is 27.9 plus 32.1 times. The other one is values are opposite. VB is higher. VB is higher. Sorry. VB is higher. VB is higher again. Pressure at B is lower. So this should be in the opposite side. From here. See? Opposite. VB is higher. VB is higher again. PB is lower. So PA minus PB comes. PA minus PB equals half rho. This will be VB squared minus VA squared. Right? So which means PA minus PB equals half rho is 1.3. VB 32.1. 32.1 squared minus 27.9 squared. That's a difference of two squares. Half times 1.3, and this can be written as 32.1 minus 27.9 times 32.1 plus 27.9. Right? PA minus PB equals half 1.3 and 32.1 minus 27.9 කියන්නේ 28 කියන්නේ 4.2. 4.2, and this is 28 and 32 yani 60 60. Simplify this. PA minus PB comes. Pressure difference PA minus PB. Then 30 1.3 times 4.2. 1.3 times 4.2 into 30. 163.8. 163.8. 163.8 pascals. That's the pressure difference. 163.8. 60. 163.8 pascals. That is the pressure difference. Next. Next. Find the pressure difference at find the horizontal force on the ball due to above pressure difference. Horizontal force F equals P. Right, I'll be erasing this now. Okay, if you need the pressure difference, force, if you need the force, apply F equals PA. Right. What's the part? 4 part 2. Question 4 part 2. 4 part 1. This is 4 part 2. F equals delta P A. Right. We need force. Delta P is here. 163.8. And area of the ball is the cross-sectional area, perpendicular area, because we are writing pressure. What is needed for pressure is the perpendicular area or cross-sectional area, right? Perpendicular area. There is a circle given 5r squared. Pi is given as 3, right? R squared given 3.5 times 10 to the power minus 2 whole thing squared. I have to simplify this. This will be 163.8 times 3 times, this is 3.5 squared 10 to the power minus 4. Simplify this. And 3.8 times 3 times 3.5 squared that is 0.6 kilo. This is 0.60 newtons. 0.6 newtons. 3. Draw the change of path of the ball due to above force when viewed at the top. Now this is the top view. This is the top view. Now according to that top view, we know A is here and B is here, right? Pressure is higher at A. Always force due to pressure difference exerts from high pressure to low pressure. A to B, then it should be exerts from high pressure to low pressure, right? So the force will be from high pressure to low pressure like this. Draw the change of the path. Okay, then velocity is like this. So the change of path is due to this force, there will be an acceleration in that direction. So change of path is like this. This is the change of path, right? Change of path. Question 5. Part 5. If the ball is released from the hand of the bowler at a height 1.8 meters from ground, what is the horizontal distance along the direction of ball is thrown? The ball hits on the ground from the bowler. Horizontal distance. So the horizontal distance is the range of the projection, because it will be a projectile motion. If the ball is released from the hand 1.8 meters above from ground, what's the horizontal distance along the direction of ball? Right. So that will be a projectile motion hereafter. Right. Now the ball is released. This is the ground. This is the ground. This is clear in that given diagram. Diagram is given. This is 1.8 meters. This is 1.8 meters. Right. And ball travels in this kind of a path. So this is what I need. Horizontal distance. Okay. And velocity here is 30, but that is horizontal. So what you can do is apply S equals U. Sorry, we need time first. Time is not task, but we have to have time. S equals UT plus half AT squared downwards first. S is 1.8. U is 0 because we are applying vertically. Horizontal velocity is there. So this is half G10 T squared. 1.8 equals 5 T squared, which means T squared equals 0.36. So T is 0.6 seconds. If time is known, use S equals ut horizontally. S will be R now. U is 30 and time is 0.6, which means R equals 18 meters. 18 meters. Then, if the ball hits the ground as shown in the figure, find the displacement d for the ball perpendicular to the direction of ball is thrown. All right. 6. Okay, now first we can find the horizontal acceleration, right? Horizontal acceleration. Horizontal acceleration. Use F equals ma horizontally. Horizontal force on the ball is this 0.6. And mass of the ball, I think it's given. Mass of the ball, 150 grams. Mass of the ball, 150 grams. 150 grams 10 to the minus 3 A. So A will be, this is 10 to the power 3 again, 1, 2, 3, 600 over 150, which means this is 4. 4m is minus 2. All right. Yeah, 600 over 150, 4m is minus 2. Horizontal displacement can be determined. Horizontal displacement. Again, use S equals UD horizontally. Yeah. S will be D, and there is no U here. Sorry, UT plus half AD squared. Because this horizontal displacement is to this direction. Right? F and acceleration is also to this direction. So this third is again being perpendicular. So it is neglected. 0 plus half acceleration is 4 in that direction. Time will be same 0.6 squared. Right? Simplify this. 2 times 0.6 squared is 0.36. So D is 0.72. D is 0.72 meters, which means D is 72 centimeters. 0.72 meters, 72 centimeters. Right? That's all. That's all from the tute. That's all from the tute. Right. That's all from the tute. Right. So other than that, listen, now first take this down. And if you got any questions, please ask. Right. Okay. And other than this, these calculation sums, you have to know the explanations using Bernoulli's theorem. Explanations. So I'll be showing you one explanation as well. Right? Explanation type questions are coming. Right? Now, as an example, let's say, look at here. As an example, let's say, See, as an example, let's say you need to explain a scenario where why or how the ball is swing according to Bernoulli's theorem, right? අපි මේ question එක කරපු එකම explain කරලා බලන්නම්කෝ. Right? Explanations. Right? So let's say you are asked to prove how this ball is getting swing, how this ball is swing according to Bernoulli's theorem, right? So when it comes to explanations, this is how an explanation is done. See, this is how an explanation is done. So let's say this diagram is given. Let's say this diagram is given. Let's say this velocity and vertical velocity. Let's say velocity of the ball is given like this. Velocity of the ball is given like this, v, and tangential velocity is also given, omega, right? And you are asked to explain how this ball is getting swing, in swing or out swing using Bernoulli's theorem, right? This is how it is done. First, check these velocities. Now you know linear velocity will be same throughout. So at this point and this point also, that will be same. And when it comes to tangential velocity is along the tangent. So here it will be along the tangent as r omega, and here it will be along the tangent as r omega. Now, resultant velocity at this point is v plus r omega. Resultant velocity here is v minus r omega, right? Which means now you can clearly see the resultant velocity here is v plus r omega. Resultant velocity here is v minus r omega. So which means you can clearly see now higher velocity is at here. Higher velocity is here. If higher velocity is here, for the respective layer of air also, the velocity is higher, right? And when we draw streamlines, sometimes you will be asked to draw streamlines. If you draw streamlines, the streamlines are drawn like this. Higher the velocity, closer the streamlines. Higher the velocity, closer the streamlines. Lesser the velocity, the distance between streamlines will be higher, right? So like this, you can draw streamlines as well. Like this, you can draw streamlines as well, right? Now this side, velocity is higher. So we know when velocity is higher, pressure is lower. This side, velocity is lower, so pressure is higher. And always force is exerted from high pressure to low pressure. So that's the basic explanation behind any Bernoulli's explanation, right? Velocity is check karanna, pressure is check karanna. It has a force again argue karanna, and force is always from high pressure to low pressure, right? So this is the point. Let's say these points are A and B, right? So what you can argue is this: velocity at A is higher, therefore pressure at A is lower, right? And second point, velocity at B is lower, so pressure at B is higher, right? Force due to pressure difference, this is the explanation. Force due to pressure difference is from high pressure to low pressure. Right? Which means the force is from B to A, right? PB greater than PA, right? PB greater than PA. So the pressure that the force exerts from, therefore, force exerts from B to A. Force exerts from B to A. Now force is from B to A. B is here. The force is from B to A. So with this force, deviation of the ball or the swing of the ball is going to be like this. Swing of the ball is going to be like this. Right? So likewise, you can do an explanation using Bernoulli's theorem, right? And as another example, let's say this is example 1. And as another example, see, if I need to explain how this how this roof of this house blow off when a wind is blown, something like that. These are the using applications or use cases of Bernoulli's theorem, right? So if this is asked, again, this is the thing. So when a wind is blown, the wind is blown like this. See, the wind is blown like this. If a wind is blown, right? If wind is blown from left to right, it will be like this. Now with this wall, it will be blocked, and velocity at air inside home is inside this house is 0. So let's say all doors and windows are closed. Right now velocity will be 0. But here velocity is non-zero. This is higher velocity. Higher velocity means low pressure. And low velocity means this low velocity means high pressure. From high pressure to low pressure, the force exerts. Now with that force, what happens is the roofs will go off. Roofs will blow off from the house. So that is how roofs are blown off using Bernoulli's theorem. So likewise, if a scenario is given to you to explain, right, what you can do is you can use velocities, pressures, etc. use කරන්න තියෙන්නේ. Velocity එක බැලුවා, pressure එක බැලුවා, force එක බැලුවා. You know, if velocity is higher, pressure is lower, and always force exerts from high pressure to low pressure only. So with that, explain it. That is called an explanation from Bernoulli's theorem, right? Okay, take down if there's anything. Take down if there's anything. Right, take down if there's anything. All right. So basically that's all. What you have to know about fluid dynamics to tackle any question, right? We discuss even explanations, right? So that's everything you need to know about fluid dynamics. To tackle questions and to deal with fluid dynamics, right? Now, if you are in this live, if you watch the live from beginning to the end, even if you didn't know anything about fluid dynamics at the beginning, now I know you know everything about fluid dynamics. So practice more questions and make yourself comfortable, make yourself more comfortable by fine-tuning these skills and enhance your confidence of these questions, right? Okay, then yeah, so we have come to the end of the question discussion now. Any questions before winding up? All good? And the students who were in this live from the beginning, now once the live is ended, once this live video is ended, you can add a comment to this video whether you understood the lesson, whether you understood the discussion or not, right? So I can watch it later whether you have understood or not. Anyone who is watching the live, and if you have got something from this, right? Doesn't matter whether you are a regular class student or not, right? If you got something from the video, if you understood what we discussed, add a comment to this video after this live stream is ended, because live chat will be disappeared after the chat after the live stream is ended. So therefore, add a comment, right? No any questions, ne? Okay, right. So since there are no questions, so we'll wind up here. So that's the end. That's it for today. You can check into my Telegram and WhatsApp channels for all updates coming up. So if there are any other free sessions or free seminars, something like that, I can give you all updates on channels and channels and groups, right? Okay, then yes. So it was around 3 hours. It was around a 3 hours discussion of questions entirely from fluid dynamics, and this is the end. So make maximum out of this. Take maximum out of this and practice these questions more. And if you are facing A levels this year, this will be highly useful. And if you are a 26 student also, so make yourself comfortable with these questions before you have because you have 1 year and 2 months around time to the exam, right? Okay then. So then that's the end. That's the end. So I'll finish it off here. See you all in the next class, right? Good night and goodbye. Yeah, that's the end. Goodbye.